Hello everyone. Welcome to the Learn Circuit tutorial. In this video, we will learn node analysis, a method to solve node voltages. The main concepts are the follows. Node, a point in a circuit where two or more circuit elements meet. Reference node, where the voltage is assigned 0 volt. Node voltage, the electrical potential difference between a node and the reference node. For example, in the following circuit, Node 1 is the point where the resistors 1 and 3 meet. Node 2 is the point where the voltage source 1 and resistor 1 meet. Similarly, the circuit has Node 3 and Node 4. In order to define the node voltages, we need a reference node. The reference node can be any node, but we typically select the node with the most connections as the reference node, normally the bottom node in a circuit. For example, in the following circuit we select node 4 as the reference node. Then assign its voltage equal to 0 volt. We also draw a ground sign. We then assign node voltages to non-reference nodes, namely V1, V2, and V3. Furthermore, because the first voltage source directly connect the reference node and node 2, that will make the voltage of node 2 equal to 6 volt. This is because V2 minus V4 is 6 volt. Likewise, V3 minus V4 is 3 volt. It makes the voltage of node 3 equal to 3 volt. Alright. For this example, the only unknown voltage is V1. The node analysis method is used to solve for unknown node voltages. Now let's dive into it. The steps of the node analysis method are the follows. Step 1. Select a reference node and label non-reference node voltages. Step 2. Label current directions and write KCL. Step 3. Solve the system of equations. Now let's see an example. This is the same circuit we used to explain the concepts. We need to determine the node voltages and branch currents. Step 1 is to select a reference node and label non-reference node voltages, which was already done when we explained the concepts. There are two comments I want to make here. The first one is that you don't have to label V2 and V3 because we know their node voltages. They are labeled here for demonstration purposes. The second comment is that some students are confused by 3 nodes in the bottom of the circuit. However, the entire bottom is connected by wires, so they are considered as a common node or single node. Alright, let's move to step 2, label current directions and write KCL. There are 3 branches connected to node 1. We need to label the current directions for each branch, and a branch has 2 ways to label the direction, enter or leave the node. In total, there are 8 ways to label them. You should not spend much time on this, because we will get the same equations regardless of the current directions. Let's label the current directions like the way shown in the circuit. I will show you another way later. You will see that we will get the same equations. Now let's write KCL for node 1. But what is KCL? KCL stands for the Kirchhoff's current law. There are quite a few ways to write a KCL. The most intuitive way is that the summation of currents entering a node is equal to the summation of currents leaving that node, as indicated as equation A. If we move the summation of leaving current to the left, it becomes equation B. If we move the summation of entering current to the right, it becomes equation C. If we define all the currents entering the node, it becomes equation D, in which we assume the current leaving the node is negative. If we define all the currents leaving the node, it becomes equation E, in which we assume the current entering the node is negative. These are the 5 equations for writing a KCL. But I hope you realize that they can derive from each other. Equation A is very easy to memorize, but it is not very practical for writing KCL because you need to group the entering currents and leaving currents first. I typically use equation B to write KCL, but you can just pick either equation B or C. Equations D and E are special scenarios in which all the currents are labeled to enter or leave the node. Let's use equation B to write the KCL for node 1. We will have I1 minus I2 plus I3 equals 0. Note that there is a negative sign in front of I2 because they are leaving the node. There are positive signs in front of I1 and I3 because I1 and I3 enter the node. But what are we solving? Remember that in the node analysis method, we solve node voltages. We need to express the currents in terms of the node voltages. We can use Ohm's law to do so. For example, I1 equal to VR1 over R1. From the circuit, we can see that VR1 equals to V2 minus V1. A common question here is that why VR1 equal to V2 minus V1? Why not VR1 equals to V1 minus V2? The short answer is because of the current direction we defined. I will answer this question later, before too many interruptions. Then, we can write I1 equals V2 minus V1 over R1, where V2 is 6 volt. Similarly, we can determine I2 equals V1 minus VG over R2, where VG is 0 volt, and I3 equals V3 minus V1 over R3, where V3 is 3 volt. Finally, we can substitute I1, I2, and I3 into the original KCL equation to work the final KCL equation. After some practices, I hope you can directly write this equation from the circuit instead of starting from I1 minus I2 plus I3 equal to 0. In step 3, we solve the equation. V1 equals to 2.25 volt. Then, we can solve all the branch current using Ohm's law as follows. You can also verify the KCL equation using the calculated currents. We have learned the main concepts and steps of nodal analysis. I think I left 2 questions not answered. Question 1 is how to relate the resistor voltage to their terminal voltages or node voltages. Question 2 is how to define the current directions. Let's start with the first question by revisiting our example 1. In this example, we expressed VR1 equal to V2 minus V1 instead of V1 minus V2. Similarly, we expressed VR2 equal to V1 minus VG instead of VG minus V1, and expressed VR3 equal to V3 minus V1 instead of V1 minus V3. The short answer is that for R1 we labeled the current direction from left to right. So basically we assumed V2 is greater than V1. Therefore, VR1 equal to V2 minus V1. Likewise, for R2 we labeled the current direction from up to down. We assumed V1 is greater than ground voltage. Therefore, VR2 equal to V1 minus VG. For R3 we labeled the current direction from right to left. So we assumed V3 is greater than V1. Therefore, VR3 equal to V3 minus V1. Essentially, we are following the passive sign convention, which indicate that the current enters positive terminal of the components. Now let's use the passive sign convention to explicitly label the voltage polarities across the 3 resistors. For R1, the current enters the left, so the left terminal should be labeled as positive, and the right terminal is negative. Similarly, for R2, we need to label positive polarity at the top and negative polarity at the bottom. For R3, we need to label positive polarity at the right terminal and negative at the left terminal. Once the voltage polarities are labeled, it is clearer that the resistor voltages are equal to the node voltage at the positive terminal minus the node voltage at the negative terminal. It is noted that you do not need to label polarities when you use nodal analysis. The polarities are labeled here for demonstration purposes. The passive sign convention is very important. Therefore, let me explain it a bit further. Using the passive sign convention keeps the following things consistent. Number 1, it makes writing KCL and KVL consistent. Number 2, it can be used to figure out who's supplying or absorbing power. The second point need a separate treatment. Now let us focus on KCL and KVL. We know that both the voltage and current have two pieces of information. Voltage has magnitude and polarity, and current has magnitude and direction. The magnitude of voltage and current is related by Ohm's law. The Ohm's law equations are used in all the circuit analysis methods. For example, KCL for nodal analysis and KVL for loop analysis. But how are the voltage polarity and current direction related? The answer is the passive sign convention that indicates the current enters positive terminal of passive components, namely resistors, inductors, and capacitors. We will learn inductor and capacitor in AC network. Let us focus on resistors for now. If the current direction is given like shown in figure B, how would you label the voltage polarity? You can pause the video for a second. Because the current enters the positive terminal of the resistor, we need to label the positive polarity at the right side and a negative polarity at the left side. Did you do it right? What about the one shown on figure C? For the same reason, we should label the positive polarity at the left side and a negative polarity at the right side. Therefore, at the moment we label the current direction, we have also decided the voltage polarities, which are determined by the passive sign convention. For this reason, when using nodal analysis or loop analysis, we do not need to label voltage polarities explicitly. The situation shown in figure A is what we usually encounter, where none of the voltage polarities or the current direction is labeled. So, you are the boss determining it. If you change the current direction, the voltage polarities will also change. Along the current direction you labeled, the voltage across a resistor is always drop. Therefore, at the end, you will get the same KCL or KVL regardless of how you label the current direction. I will show you this by answering the second question. What if voltage polarities or current direction of some resistors are given in the circuits? For example, for the left circuit, we need to determine the current I/O. Its current direction is labeled in the circuit. For the right circuit, we need to determine the voltage VO. Its voltage polarity is labeled in the circuit. While if they are given, we just use them. For the left circuit, the current direction of the middle branch is already labeled. You only need to label the current directions for the other branches. Less work to do, right? For the right circuit, once the voltage polarity is given in the circuit, then essentially, the current direction is also given based on passive sign convention. You should label it in such a way, meaning the current enters the positive terminal of R4, then the current should flow from the top terminal to the bottom terminal of R4. Let's move on to the second question. How do we define the current directions? The short answer is that it does not really matter how you label the current directions, because as mentioned earlier, you will get the same KCL equations regardless of the labeled current directions. Let us use the same example to see two ways of labeling the current direction. The current directions are labeled differently in the two circuits. For example, in the left circuit, the first branch current is labeled as entering node 1, denoted as I1A. However, in the right circuit, the current is labeled as leaving node 1, denoted as I1B. For the second branch current, the current in both circuits are labeled leaving the node 1, both denoted as I2. For the third branch current, the left circuit is labeled as entering node 1, denoted as I3A. In the right circuit, the current is labeled as leaving node 1, denoted as I3B. In fact, in the right circuit, all the currents are labeled as leaving node 1. Now, let us see how the KCL equations are derived in both circuits. For the left circuit, we will use equation B. The KCL equation at node 1 is as follows. Then, we rewrite the equation using node voltages. For the right circuit, we will use equation E. The KCL equation at node 1 is as follows. Then, we rewrite the equation using node voltages. You may pause the video to check the equations. Let us do 2 further algebra steps for the left equation. As can be seen, we had the same KCL equation, regardless of the labeled current directions. Let us take the 2 steps back and compare the 2 ways of labeling the current direction. The second way, namely label all the currents flowing away from the non-reference nodes, has the following advantages. All the terms added together equal to 0. No subtraction, as can seen in the left equation. In addition, the node voltage V1 is the leading variable of all the terms. Compared with the left equation, V1 is leading in the second terms, but not leading in the first and third terms. Then, by labeling all the current flowing away from the non-reference node, you will have little chance to make mistakes. Now, let us see the solution of the circuit. The 2 methods give us exactly the same solutions. As we know, both the voltage and current have 2 pieces of information. Voltage has magnitude and polarity, and current has magnitude and direction. We selected the same reference node in both circuits, so both the magnitude and polarity of V1 in the 2 circuits are the same. The magnitudes of the currents in branch 1 are negative relative to each other. However, their directions are also opposite. Therefore, combining the magnitude and direction, the 2 currents are exactly the same. It has to be the same because the 2 circuits are identical, and the current in the first branch has to be physically the same. This also applies to I3A and I3B. For the middle branch, the current directions are both labeled from up to down, so their directions and magnitude are both the same. Let us summarize. In this video, we learned the main concepts of node analysis. We then learned its major steps. We also learned the passive sign convention. Finally, we discussed how to label the current directions. That's it for this video. I hope you find it helpful. If you have any questions, please leave a comment below. Thank you for watching. Visit learncircuits.net for more information. See you next time.